A crystal structure can be formed by parallel displacements of a portion of it. The smallest, regularly repeating portion is a primitive cell. In the following figure, the black dashed quadrilaterals are not repeating portions. The black solid quadrilaterals are repeating portions but not the smallest. The red solid quadrilaterals are smallest repeating portions. They are primitive cells. In two-dimensional space, the primitive cells are parallelograms. In three-dimensional space, the primitive cells are parallelepipeds. The vectors pointing from one vertex of a primitive cell to the nearest vertices are primitive translation vectors, denoted as A1, A2, A3, or A, B, C, etc. So, a primitive cell and a set of primitive vectors have one-to-one correspondence. A Bravais lattice is an infinite array of discrete points generated by a set of discrete translations described by the linear combination of the primitive vectors, whose coefficients are integers. Thus, a lattice and a set of primitive vectors have a one-to-one correspondence. And a lattice and primitive cell have a one-to-one correspondence as well. Each primitive cell shares 2 to the power of n lattice points at the vertices with 2 to the power of n primitive cells. So, each primitive cell contains exactly one lattice point. All lattices have some symmetries other than translational symmetry. For example, a two-dimensional oblique lattice is such a lattice, whose magnitudes of primitive vectors are not equal and the angle between them is not 60, 90 or 180 degrees. An oblique lattice is symmetric with respect to rotation by 180 degrees. In general, all two-dimensional lattices are symmetric with respect to rotation by 180 degrees with respect to every lattice point and the center of every primitive cell. A two-dimensional rectangular lattice is such a lattice, whose magnitudes of primitive vectors are not equal and the angle between them is 90 degrees. The primitive cell of rectangular lattice is rectangle. A rectangular lattice is symmetric with respect to reflections with respect to lines which are parallel to the primitive vectors and contain or bisect the primitive vectors. A two-dimensional square lattice is such a lattice, whose magnitudes of primitive vectors are equal and the angle between them is 90 degrees. The primitive cell of square lattice is square. A square lattice is symmetric with respect to rotation by 90 and 270 degrees with respect to every lattice point and the center of every primitive cell. A square lattice is symmetric with respect to reflections in 4 directions. A two-dimensional hexagonal lattice is such a lattice, whose magnitudes of primitive vectors are equal and the angle between them is 60 or 120 degrees. The primitive cell of hexagonal lattice is rhombus. A hexagonal lattice is symmetric with respect to rotation by 60, 120, 240 and 300 degrees. The full symmetry of hexagonal lattice is not obvious from the rhombus primitive cell but is obvious from the hexagon. A hexagonal lattice is symmetric with respect to reflections in 6 directions. If the magnitudes of primitive vectors are equal and the angle between them is not 60, 90 or 120 degrees, the primitive cell is rhombus. The lattice is symmetric with respect to reflections in 2 directions like rectangular lattice. However, the calculation based on rhombus primitive cell is not very convenient. For each lattice, a conventional cell has been chosen on a case-by-case basis by crystallographers based on convenience of calculation. These conventional cells may have more than one lattice points. For example, the conventional cell of lattice with rhombus primitive cell is rectangle with one more lattice point at the center. So, this conventional cell contains 2 lattice points. The area of this conventional cell is twice of that of the primitive cell. From the conventional cell, the full symmetry of lattice is obvious. For example, the rectangle has the same symmetries as the rhombus. A unit cell may refer to a primitive cell or conventional cell if the latter exists. The lattice is named after the shape of the unit cell. So, this lattice is called centered rectangular lattice. Lattice vectors are the vectors pointing from one vertex to the nearest vertices of a unit cell. The lattice vectors are usually denoted as A, B, C, etc. Lattice constants are the magnitudes of lattice vectors and the angles between them. The angles are usually denoted as theta, alpha, beta, gamma, etc. A lattice system is a group of lattices with the same symmetry. In other words, lattices in a lattice system have the same shape of unit cells, i.e., the same properties in their lattice constants. In two-dimensional space, the 5 lattices are grouped into 4 lattice systems. The monoclinic, tetragonal, and hexagonal lattice systems have 1 lattice each, oblique, square, and hexagonal. The orthorhombic lattice system has 2 lattices, rectangular and centered rectangular. For example, graphene is a typical two-dimensional crystal. The unit cell is rhombus, and the angle is 60 degrees. So, the lattice for graphene is hexagonal. Each unit cell of graphene contains 1 lattice point but 2 carbon atoms. In three-dimensional space there are 14 lattices. These are obtained by combining one of the 7 lattice systems with one of the centering types. The centering types identify the locations of the lattice points in the unit cell as follows. Primitive, lattice points on the cell corners only. Base-centered, lattice points on the cell corners with 1 additional point at the center of each face of 1 pair of parallel faces of the cell. Body-centered, lattice points on the cell corners, with 1 additional point at the center of the cell. Face-centered, lattice points on the cell corners, with 1 additional point at the center of each of the faces of the cell. Not all combinations of lattice systems and centering types are needed, as several of these are in fact equivalent to each other. In general chemistry, only the cubic and hexagonal lattice systems will be discussed. The cubic lattice system is a lattice system where the unit cell is in the shape of a cube. This is one of the most common and simplest shapes found in crystals and minerals. The primitive cubic lattice consists of 1 lattice point on each corner of the unit cell. Each lattice point is then shared equally between 8 adjacent unit cells. Therefore, the unit cell contains in total 1 lattice point. Coordination number is the number of nearest neighbors of a lattice point in the structure. In primitive cubic lattice, a lattice point has 6 nearest neighbors. So primitive cubic lattice has coordination number 6. The body-centered cubic lattice has 1 lattice point in the center of the unit cell in addition to the 8 corner points. It has a net total of 2 lattice points per unit cell. The coordination number is 8. The lattice points at the corners and at the body center are equivalent. It is because each point is at the corners of 8 unit cells, but also at the center of another unit cell. The vector connecting the corner and the center is one of the primitive vectors. The face-centered cubic lattice has 6 lattice points on the faces of the cube, each of which gives exactly 1/2 contribution in addition to the corner lattice points. So, face-centered cubic lattice has a total of 4 lattice points per unit cell. The lattice points at the corners and at the face centers are equivalent. It is because each point is at the corners of 8 unit cells, but also at the face centers of other unit cells. The vector connecting the corner and the face centers are the primitive vectors. Each point is at the centers of 3 perpendicular faces, in which it has 4 nearest neighbors at the face corners. So, the coordination number of face-centered cubic lattice is 12. The unit cells of some crystals are shown. For example, in calcium fluoride, the white balls form FCC structure. So, there are 4 white balls per unit cell. On the other hand, all the yellow balls are inside the unit cell. there are 8 yellow balls per unit cell. Thus, the ratio of the white to the yellow balls is 1 to 2. Therefore, the white ball is calcium. The yellow ball is fluorine. A fluorine atom is surrounded by 4 calcium atoms. Its coordination number is 4. A calcium atom is surrounded by 8 fluorine atoms. Its coordination number is 8. Crystals have certain special properties related to the anisotropy of the crystal, i.e., the lack of rotational symmetry in its atomic arrangement. For example, graphite crystals consist of a stack of graphene sheets. Although each individual sheet is mechanically very strong, the sheets are rather loosely bound to each other. Therefore, the mechanical strength of the material is quite different depending on the direction of stress. Vectors and planes in a crystal lattice are described by the 3-value Miller index notation. This syntax uses the indices h, k, and l as directional parameters. The syntax denotes a plane that intercepts the 3 points at A over h, b over k, and c over l, and multiple thereof. If one of the indices is 0, it means that the planes do not intersect that axis, i.e., the intercept is at infinity. For example, Miller index 1, 0, 0 describes the plane that are parallel to b and c, and intersect at integer multiple of a. Miller index 2, 0, 0 describes the plane that are parallel to b and c, and intersect at integer multiple of 1/2 of a. Miller index 1, 1, 0 describes the plane that are parallel to c, and intersect at same integer multiple of a and b. Miller index 1, 0, 2 describes the plane that are parallel to b, and intersect at same integer multiple of a and 1/2 of b. Negative indices are indicated with horizontal bars. For example, Miller index -1, 1, 0 describes the plane that are parallel to c, and intersect at the same integer multiple of -a and b. Crystallographic planes are planes linking nodes, which are atoms, ions, or molecules. Different planes have different arrangements of nodes. The arrangements of node on the planes have an influence on the behavior of the crystal. For example, the points on the 1, 0, 0 plane of face-centered cubic structure forms a 2-dimensional square lattice. The points on the 1, 1, 0 plane of face-centered cubic structure forms a 2-dimensional rectangular lattice. The points on the 1, 1, 1 plane of face-centered cubic structure forms a 2-dimensional hexagonal lattice. In an orthogonal coordinate system for a cubic cell, the Miller indices of a plane are the Cartesian components of a vector normal to the plane. The spacing between adjacent lattice planes can be calculated with Miller indices as well. Light is electromagnetic wave. Atoms scatter light waves primarily through the atom's electrons. Just as an ocean wave striking a lighthouse produces secondary circular waves emanating from the lighthouse, a light wave striking an atom produces secondary spherical waves emanating from the atom. When light of a wavelength comparable to atomic spacing strikes a plane of atoms, it undergoes constructive interference when it is scattered in a specular fashion, mirror-like reflection. In X-ray diffraction, X-rays scattered from adjacent planes will combine constructively, constructive interference, when the angle between the plane and the X-ray results in a path length difference that is an integer multiple of the X-ray wavelength. This equation, called Bragg's law, was first proposed by Lawrence Bragg and his father, William Henry Bragg, in 1913. In a typical XRD pattern, the horizontal axis is the angle between the incident and scattered X-ray. The vertical axis is the scattering intensity. Each peak in XRD spectrum corresponds to a set of lattice planes, denoted by the Miller indices. For example, both silver and silver chloride have cubic crystal system, so their XRD spectra have the same patterns. However, since silver chloride has bigger unit cells, the diffraction angles of silver chloride are smaller than those of silver for the same Miller indices. XRD was used in determining the double helix structure of DNA. In May 1952, Raymond Gosling, a graduate student working under the supervision of Rosalind Franklin, took an X-ray diffraction image, labeled as Photo 51, at high hydration levels of DNA. This photo was given to Francis Crick and James Watson by Maurice Wilkins and was critical to their obtaining the correct structure of DNA. In 1962, after Franklin's death, Watson, Crick, and Wilkins jointly received the Nobel Prize in Physiology or Medicine. Atomic packing factor, APF, is the fraction of volume in a crystal structure that is occupied by constituent particles. In atomic systems, by convention, the APF is determined by assuming that atoms are rigid spheres. The radius of the spheres is taken to be the maximum value such that the atoms do not overlap. For one-component metals, the lattice points are the centers of the atoms. For primitive cubic lattice, the number of atoms per unit cell is 1. The side of the unit cell is of length 2r, where r is the radius of the atom. The APF is about 0.52. For body-centered cubic lattice, the number of atoms per unit cell is 2. Each corner atom touches the center atom. A line that is drawn from one corner of the cube through the center and to the other corner passes through 4r. By geometry, the length of the diagonal is square root of 3a. Therefore, the APF is about 0.68. For a face-centered cubic lattice, the number of atoms per unit cell is 4. A line can be drawn from the top corner of a cube diagonally to the bottom corner on the same side of the cube, which is equal to 4r. Using geometry, the length of the diagonal is square root of 2a. Therefore, the APF is about 0.74. Close packing of equal spheres is a dense arrangement of congruent spheres in an infinite, regular arrangement, or lattice. The problem of close packing of spheres was first mathematically analyzed by Thomas Harriot around 1587, after a question on piling cannonballs on ships was posed to him by Sir Walter Raleigh on their expedition to America. The close packing of equal spheres in two-dimensional layer forms hexagonal lattice. Relative to the first layer with positioning A, two sets of positionings, B and C, are possible for the second layer. Suppose the second layer is positioned on B, and the third layer is positioned on C. Then, the stacking is repeated in the pattern of ABC, 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 etc. Every third layer is the same. This close packing is the same as FCC structure. So, FCC is also called cubic close packing, CCP. FCC has the highest APF for one component substance. Alternatively, the third layer can be positioned on A, and the stacking is repeated in the pattern of AB, 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 etc. Every other layer is the same. This structure is called hexagonal close packing, HCP. The coordination number of HCP is 12, the same as FCC. And the APF of HCP is the same as FCC as well. However, unlike the FCC, HCP is not a Bravais lattice, as there are two inequivalent sets of points. Instead, it can be constructed from the hexagonal Bravais lattice by using a two-atom motif associated with each lattice point. For elements that are solid at standard temperature and pressure, the table gives the crystalline structure of the most thermodynamically stable forms in those conditions. Most metals form one of the close packing structures because dense packing and high coordination number reduce the total energy.